Okay, now I'm going to move along to example 5 in your 3.9 notes handout. So for example 5, it says a lamp pole is 10 feet tall. A person 6 feet tall walks away from the lamp pole at 4 feet per second. How fast is the tip of the shadow moving when the person is 10 feet away? Okay, so for this we should see, or hear I guess, that we have several things going on. No matter what, I need to write down what I know and what I want. This one's a little bit more abstract to think about, so I'm going to draw a picture just to think about what this looks like. Okay, so thinking about what we know. Right, we know that we have some lamp pole. Okay, so we have some lamp pole. I'm just going to draw it like this. And I know this lamp pole is 10 feet tall. Okay, it should be pretty clear that if our lamp pole is 10 feet tall, that is not going to change. So this is definitely constant, just like the ladder was. You know the length of your lamp pole is not going to change. So this is constant. Okay. It also tells us that a person that's 6 feet tall is walking away. Okay, so I also know that I have a 6 foot tall person. Okay, and unless something real crazy happens, this person is not going to suddenly shrink or grow while they're walking, so this is constant as well. Okay, so now we got this person. Let's say he's, here's a lamp pole. He's walking, however long, we don't know, but he or she, or anything, this person, I'll say, is 6 feet tall. Okay, walks away from the lamp pole at 4 feet per second. So now I know that I have to give a name for something because I'm given a rate. So if this person is walking away, they're walking, I'm just going to call this distance that they have walked x. So x is going to be the distance they have walked, and I'm given that dx dt, so how fast they're walking this distance, is equivalent to 4 feet per second. Okay, so I have all of my known information right here. Took care of that second sentence. Let's move on to the third sentence, which asks, how fast is the tip of the shadow moving along when the person is 10 feet away? Okay, so now I need to think about what I want. Okay, so what I want. Okay, and this is a little bit more complex. So if we're thinking about this question, this is our lamp pole right here. Imagine we have some light kind of shining down from this lamp pole. So the light's shining down. This is the top of the person's head. And if you think about it, when there's a light behind you and you look in front of you, it's going to cast some shadow. So this light is going to shine down and it's going to cast a shadow. So let's say we have some little distance here. Okay, I don't need to know what that is, but I need to think about my shadow. So I'm going to do this whole distance. I'm going to call this L. So L is what I'm using to represent my shadow length. The reason I want it to be this whole distance on the bottom of my triangle is because I need to erase this in a minute. But if you think about it, if I wanted to, I could have drawn my 6 foot person here, or here, or here, or here, or here. So if the person was, say, standing right here, then I know that shadow would really be more like right here. So it could be any of this distance, which is why I have to account for everything and why I'm drawing it there. Okay, so then I can label this if I want to. Eventually I'll need to, and you'll see why. But this little guy right here, this distance, is going to be L minus X. Okay, that's for later. But either way, we should see that what we actually want to find, is what I called L, so dl dt. And that is when X equals 10 feet, because it says when the person is 10 feet away. So when X equals 10 feet. Okay, so that takes care of the last sentence. We've pretty much drawn everything that we can, or everything we can take away from just reading the question, and now we're going to have to think a little bit more because we know that, or we should know that, we need an equation that relates X and L. So I need something to relate these two variables because I know that the rates involve X and L, so that means I have to relate these. Okay, well, this we have to think about. So like I said, some problems are a little easier because we're either given an equation or it's something we can easily remember. This, for some students, isn't as easy to remember, but if you have the right prereq skills, it's not too terrible. So if you look at the picture that we have right now, you should see that we have a big right triangle, and actually embedded inside of it, we have a little right triangle. Well, notice that when you have the two triangles, and they are the same shape or take the same form, we actually have similar triangles. So honestly, if we were in class, I would make you work for this a little bit more and say, oh, like, how could we do this? How do these relate? And you'd have to think about it more, but I'll just tell you that what's going to help us relate these two variables or these two rates is going to be similar triangles. Okay. So I'm going to use similar triangles. I'm going to do my big triangle in blue. So I'll do my big triangle in blue, although I'm drawing it slightly smaller because I don't have that much room. And I'm going to do my little triangle in green. All right, so I'm just pulling these from my first image, this being my big triangle right here, the blue one, and then the little triangle being my green right here. All right, so I know that these are both right angles. All right, I know that the length of this big triangle is, actually I don't know the length of that and I don't necessarily want to, but I know that the length of this whole thing, the bottom part, is L. That's supposed to be an L. Let's see, I know the height of this is always 10. I think that's about all I know about that one. And then I know the height of my little triangle is 6. And I know that the length down here is L minus X. Okay, so we should remember that when we have similar triangles, their side lengths are proportional. So we should recall the side lengths of similar triangles are proportional. Okay, so this means that if I take the ratio 10 feet over L feet, 10 feet over L feet for my big triangle, that's going to be equal to or proportional to my little triangle, which is 6 feet, 6 feet over L minus X feet. Okay, we should see here that the units all divide out to 1, so I'm really just trying to solve for the variables right now. When I do so, I can cross multiply each piece. So when I do that, I'd have a 10 times an L minus X equaling to a 6 times L. Right, from here, I'm going to distribute my 10 through. When I do so, I get 10L minus 10X equals a 6L. Right, now just to simplify this a little bit, I will combine like terms. So I'm going to subtract the 6L to the left, and I'm going to add the 10X to the right. So when I do that, I would get, let's see, a 4L equaling to a 10X. And now you can see I have a nice, clean, simple equation that relates my two variables, which are involving of my two rates, L and X. So from this point, I can see that I'm at a good place to take the derivative. So taking the derivative of each side with respect to what it requests, which is t, as we can see at the beginning, I'm going to get 4, that's just a constant multiple, so I can just pull it out in front, 4 times dl dt, the derivative with L with respect to t is dl dt, equals 10 times dx dt. Right, so that's looking good. Now that I have my rates, I can go ahead and take the derivative of each side. Well, I already took the derivative. Sorry, I can just solve for what did I want? dl dt? Yeah, we wanted dl dt, so I need to plug in my dx dt and solve for dl dt. Just come over here to do that. All right, so I'll divide the 4 as well. I might as well. So I get dl dt equals 10 over 4, which simplifies to 5 halves. times dx dt was given as 4 feet per second. Right, so this gives me that dl dt is equal to 4 times 5 is 20 divided by 2 is 10. So I have 10 feet per second. Thinking about if our answer is logical, well, if you think about a shadow as you walk, it gets longer in front of you if the light behind you is behind you, basically. So it makes sense that our shadow, the change in our shadow length would increase or be positive. And then, of course, the length is in feet, so it makes sense that we have feet, and this is over time per second. So thinking about our answer logically, it definitely makes sense, which means I'm going to keep that as my final answer. Okay, I'm going to go ahead and do number 5 on here as well. And by number 5, I mean number 6, because I just did number 5. So for number 6, the first thing that I'm going to do is just read this, and then there's a quick correction that I need to make. So number 6 says the gravitational force on a rocket at a distance from the center of the Earth is given by F equals K over R squared, where K is, and this should say, so this is number 6. So this should say where K is, and that should be a 10 to the 13th, so 10 to the 13th Newton kilometers per second, which is a measure of force. Okay, then it says at the instant that R is 10 to the 4th kilometers, the rocket is moving 0.2 kilometers per second away from the Earth. How fast is the gravitational force changing at that moment? All right, so we read through this, but we still need to draw out everything that we know. Okay, so we know an equation that we're given, which is force, and I'm going to think about that in a minute, so I'll just kind of write that to the side so I know I'm actually just given this equation. I'll write it right here. Okay, so I'm given the equation that F is equal to K over R squared. All right, and then this tells me that K, which is a constant, so tells me that the constant K is equal to 10 to the 13th Newton kilometers per second. So this is a constant. All right, that takes care of that first sentence. At the instant that that R is 10 to the 4th kilometers, the rocket is moving 0.2 kilometers per second away from the Earth. Okay, so this tells us that dr dt, because it's talking about the movement in R, is 0.2, and that's kilometers per second. So kilometers per second. When it says R is 10 to the 4th. Okay, so if we're thinking about what's going on here, we have this rocket that basically started at, or on Earth, let's see, and we're trying to keep track of its distance from the center of the Earth, and that's because we're thinking about the gravitational pull of the Earth, which theoretically would be from the center of the Earth, and so this is giving us our force constant, and it's also telling us basically the rate of change at that time. The reason we have to think about the rate of change at exactly when R is 10 to the 4th kilometers is because if you think about it, as the rocket gets farther and farther away from Earth, the gravitational pull will change, which means that dr dt isn't going to be like the same the entire time. So that's why it specifies when R is 10 to the 4th kilometers, which makes sense. Okay, so now we want to think about what we actually want. So what this is asking us for. So I want. And in my last sentence, it tells me we want to find how fast the gravitational force is changing at that moment. Okay, so at the beginning of the question, it tells us that it calls F the gravitational force. So I know really what I'm looking for is df dt. And it says at that moment. So, and it says at that moment, and that moment is when R is 10 to the 4th. Okay, so r is definitely changing throughout this whole thing. If you think about a rocket taking off, it's increasing, which means its distance from Earth is changing, which means that its distance from the center of the Earth is changing, which tells us that r is changing. So it's definitely not a constant. All right, so we basically pulled everything that we can from this. Usually when I'd go through it, I'd say, oh yeah, we need an equation, but the nice part about this one is it's already given to us, so we need to use that equation. So we need to use the given equation. F equals k over r squared. Right, and if you think about it, this relates F and R. Our rates involve R and our F, so that's a good equation to use. And this is also equal to K times R to the -2. So I just did that so my derivative taking would be a little bit easier. All right, so at this point I have an equation that relates the variables that I want to involve and the rates that I want to involve, which means I can go ahead and take the derivative. I know I need to do this with respect to t because we're thinking about what's happening to this rocket and the change in radius as time goes by. So if I take the derivative with f of f with respect to t, I get df dt. All right, k is just a constant and it's actually given to me, so I can go ahead and fill that in if I want to. So k is a constant, it's given to me as 10 to the 13th Newton kilometers squared. So I just filled that in because it's a constant and a constant multiple. What I really need to focus on for my derivative taking is the r to the -2. So if I take the derivative of the outside of that, I'd have times a -2r to the -3. Now I need the derivative of the inside, which is dr dt. Okay, so from here, I am going to go ahead and fill in, that's my constant multiple, so I should probably raise this. This drops down, r is to -3, that's fine. Okay, so going through this piece, I have df dt equaling to, and then let's see, is multiplied by the constant. I'm just thinking about if my constant needs to be in my parentheses or not in, and I don't think it needs to be, so we should be good where we are here. Okay, so now I want to fill in all of my given information. So fill in our given info. Okay, so when we do that, I don't know what df dt is. I'm trying to find it, so I'm just going to rewrite df dt. Okay, I know k, my constant, which I already addressed, is 10 to the 13th Newton kilometers per second. Okay, and then I have times a -2. I know that the r that I want is 10 to the 4th, so I have 10 to the 4th kilometers, all raised to the -3rd. And then I'm given also that dr dt at the moment of time I'm looking for is dr dt, so that's 0.2 kilometers per second. Okay, so now we should see we have this big, nasty, gross equation to work with, but at the same time, we do have the df dt isolated. We don't have any unknown variables that we have to figure out, so it's actually a good thing. We just need to clean this up and make it look a little bit nicer because it's kind of sloppy as it is right now. Okay, so let's see. If I think through this part, I can see that, see, that's multiplied by that. So in my numerator, I have, let's see, the -2 was out in front of this whole thing. So I would have a -2 still here times my 10 to the 13th Newton kilometers squared. That's just all this stuff. And then I'm still multiplying by the 0.02 kilometers per second, which also remains on top. Okay, so I have that part, and then since this whole piece right here is raised to the -3, I know I have 10 to the 4th kilometers in my denominator. All right, so now I need to keep working through the rest of this. Let's combine some like terms. So -2 times 0.02 would give me a -0.4. Let's see, then we have, let's see, 10 to the 13th over 10 to the 4th, which since this is all multiplication, I can reduce or simplify by properties of exponents. So this would be times a 10 to the 13 minus 4 is 10 to the 9th Newton. And then let's see, I'm going to multiply my kilometers out up top. Okay, my computer froze just a little bit again. So as I was saying, I have the 10 to the 9th newtons from reducing 10 to the, or simplifying 10 to the 13th over 10 to the 4th. This is all multiplication and division. All right, so now here I'd have a kilometer squared times the kilometers, which is kilometers cubed, but that's divided by this kilometers down here. So I'm left with just a single kilometers. And then I see from this part, I have seconds in the denominator. So this is over seconds. Okay, and then from here, let's see. I think I missed something. I did miss something. On this part right here, this was all raised to the -3. So down here, I would actually have 10 to the 12th, because it's 10 to the 4th to the -3, which is a -12, but then it moves into the denominator, so that's 10 to the +12. And then here, 13 minus 12 is going to give us just a 10 to the 1st on that part. Okay, so then if we finish simplifying this, this ends up being a -0.04 times 10, which is just going to be a -4. And we have Newton kilometers over seconds. And we know that the rate we're looking for is df dt. Okay, so now thinking about if our answer makes sense at the end of all of this, if the rocket is taking off and we're thinking about the force, the gravitational force on the Earth for this rocket, it makes sense that as it gets farther away from the Earth, the force the Earth is going to have on it would decrease. So it's pretty logical that this is negative. And then we know that our force measurement is going to be Newton kilometers. It was given at the beginning, and if you've taken any physics, that should make some sense. And then our time is seconds. So the units also make a lot of sense here. Okay, so I'm going to have this be the last little piece just because, as long as I remember timing right, it's been close to 40 or 50 minutes, which is what we would have had in class. So when we come back to class on Tuesday, I will go over number 7 with all of you, and then we will do a worksheet for section 3.9. So over the weekend, please obviously make sure you watch these videos, which if you're hearing me say this, you should probably watch them, and then try a little bit of your 3.9 homework. So try to kind of portion it out into 2 or 3 days. So maybe try some on Monday, and then you can do a little bit on Tuesday after class, and you should have time to work on some Wednesday as well.